Okay, so in this section, we're talking dot product. The goal is to compute the dot product, to find the angle between two vectors, to compute work done, which you've done before, so moving an object a certain distance, using a certain amount of force, computing the work done there. Now, you've done that before, but the difference here is the force is not going to it's not going to be applied in the direction of travel. And so we need vectors to compute it, as you'll see. And then we're also going to compute a projection vector. So the dot product, let's say we have two vectors. If we want to represent generic vectors, if I call one u, I want you guys to make sure that you put, in the book, you can use bold print to represent a vector. But I don't know how to write with bold print and make it distinguishable from regular print. So use a little half arrow, or if you like, you can use a little hat over it. I don't care. But just use something to indicate that it's a vector that you're talking about. So that's what the half arrow is for. And then usually if I want to represent u component-wise, I'll just let the components be u subscript 1, u2, u3, and then similarly for v, v1, v2, v3. So the dot product, it's about the easiest you could hope for to compute. If you take u, here's the notation. We use a big old dot. U dot v, that's going to be equal to, you're going to multiply the corresponding components from u and v, and then add. So that's going to be u1, v1, plus u2, v2, plus u3, v3. And it really is that straightforward. That's what you do. So let's look at an example. So u is, I didn't get too creative here. U is the vector 1, 2, 3, and v is the vector 4, negative 5, 6. Let's compute u dotted with v. So I'll write out the gory details here. Normally, I would just maybe put 4 minus 10 plus 18. But let's go ahead and write the gory details. So what do I do to get the first term? I take 1 and multiply it times 4. So 1 dot, that's a little dot for regular multiplication. 1 times 4. And then I'm going to add that to, what am I going to add that to according to the definition? 2 times negative 5. So 2 times, I'll use parentheses there, negative 5. And then what am I going to add that to? 3 times 6. So plus 3 times 6. No, so normally I wouldn't show that work, because you can do that in your head if you want. So what's that? 4 plus a negative 10 minus 10 plus 18. So what does that turn out to be? 12. Okay, the dot product, we're going to have a little algebraic terminology review. The dot product, so when I say a big dot with quotes around it, I mean the dot. I didn't feel like writing out the dot product. The dot product is commutative, distributive, and associative with respect to a scalar times the dot product. So could we write that symbolically? What do I mean? Let's start with commutative. What would u dot v equal if you want to illustrate the commutative property? V dot u. And that's, I'm only going to prove one of these. That one's super easy to prove. If you just do the dot product component-wise, you'll see it breaks down to, if you go look at the definition, you could easily turn each of these products around, right? And then instead of u dot v, it would represent v dot u. But it's the same thing because real numbered multiplication, which is what each one of these products represents, real numbered multiplication is commutative too. So the proof would be very, very quick. So that's the commutative property. Oh, what about distributive? So when you represent the distributive property, you need 2 operations involved and 3 vectors and 2 operations, right? What are the 2 operations? In this case, the multiplication operation would be the dot product, and then what's the other operation? Addition. So I think we need something like this. U dotted with, we need another vector. How about v and w, v plus w? We would need something like u dotted with v plus w. Order-wise, if you actually had component form, how would you compute this first? Yeah, if you weren't using the distribution law, you could just do v plus w first, if you know what they are, and then dot product, right? But we're saying that that's the same as the good old distribution property. So what would you have to be careful? How would you want to rewrite it here? You'd want to be careful. You wouldn't want to write UV, right? And you're going to learn this as you go on in math. You have multiple operations to deal with. In this chapter alone, we have two kinds of multiplication. So you have to specify which kind of multiplication you're talking about. So there's got to be a dot in between them. So U dot V and then plus what? U dot W, yeah. So don't forget the operation. That's distributive, right? And then associative. What do I mean by that? So I said I had to give a little bit of instruction here with respect to a scalar times a dot product. So what I mean by that, let's pick a scalar like C. So suppose C is just some number, and then you have a dot product like U times V, U dot V. Then what we're saying is, let's say we take U dot V and then multiply by C. That's scalar multiplication, or that's actually regular multiplication because U dot V is a scalar, right? Then times another C. If you take C times U dot V, that's a scalar times a scalar because U dot V is a scalar. But what we're saying then is you could do it like that. You could take C times that dot product, or you could take the scalar multiplication, C times the vector U, and then dot it with V, and we're saying that's the same thing. That's the associative property. So this is the commutative property. This is good old, whoops. Let me highlight it here. This is good old distribution. And then this is the associative property. Okay, I'm not going to prove that, but you could prove it easily if you just write things component-wise. U1, U2, U3 for U, and V1, V2, V3 for V, and then C is C, and then you go through the operations, and you can show that pretty easily that that's true. Any questions there? It's important that you realize that for today, the distributive property is one of the ones we're going to make use of. Now, what do I mean by note number 2? 0 with an arrow over it, dotted with V equals 0. So this 0 is not your everyday 0, right? This is the vector. When you see 0 with a half arrow over it, we really mean the vector with components all 0, don't we? And so if you dot that vector with any vector, V, that has components V1, V2, V3, does it make sense that you're going to get just the scalar 0 as an answer? So this 0 is a scalar. Do you believe that? Yeah. Hopefully that's clear from just the definition of the dot product. And then V dot V is equal to the magnitude of V squared. That's the one I'll prove for you. So V dot V. Oh, and by the way, I'm using 3 component vectors here. Do you think these properties work just as well with vectors with just 2 components in the plane? Yeah, they work just as well with 2 components as 3. So let's prove this one. Proof for number 3. Okay, let's represent V dot V component-wise. So that would be V1, V2, V3. There's one way to represent V, dotted with V1, V2, V3. And what does the dot product say that that's going to equal? Yeah, V1 times V1, V1 squared, plus V2 squared. You're taking corresponding components and multiplying them together and add, right? So, and then plus V3 squared. And isn't that simply the square of the square root? So couldn't we write this then as the square of the square root of V1 squared plus V2 squared plus V3 squared? Would you buy that statement? Why did I write it that way? Just to irritate you? Probably. Oh, what is the square root of V1 squared plus V2 squared plus V3 squared? That's the magnitude of V. And then this exponent stays, right? So that's it. That's what we were trying to prove. Done. And pretty much all the proofs of these various properties are done in a similar way, making use of the component form of generic vectors u and v and w if necessary.